However, if data transfer is fast enough, this becomes less of an issue. Therefore, the memory capacity limitation is actually more about memory bandwidth. The concepts of compute-bound or memory bandwidth-bound were introduced in the paper Roofline, Williams et al., 2009. For mathematically, an operation can be classified as compute-bound or memory bandwidth-bound based on its arithmetic intensity, which is the number of arithmetic operations per byte of memory access. Profiling tools like NVIDIA Insight will show you a Roofline chart to tell you whether your workload is compute-bound or memory bandwidth-bound, as shown in Figure 9.2. This chart is a Roofline chart because it resembles a roof. Roofline charts are common in hardware performance analyses. Different optimization techniques aim to mitigate different bottlenecks. For example, a compute-bound workload might be sped up by spreading it out to more chips or by leveraging chips with more computational power, e.g., a higher flop/s number. A memory bandwidth-bound workload might be sped up by leveraging chips with higher bandwidth. 408 Chapter 9, Inference Optimization. 5. Prefilling effectively populates the initial KV cache for the transformer model. Figure 9.2. The Roofline chart can help you visualize whether an operation is compute-bound or memory bandwidth-bound. This graph is on a log scale. Different model architectures and workloads result in different computational bottlenecks. For example, inference for image generators like Stable Diffusion is typically compute-bound, whereas inference for autoregression language models is typically memory bandwidth-bound. As an illustration, let's look into language model inference. Recall from Chapter 2 that inference for a transformer-based language model consists of two steps, prefill ing and decoding. Prefill: the model processes the input tokens in parallel. 5. How many tokens can be processed at once is limited by the number of operations your hardware can execute in a given time. Therefore, prefilling is compute-bound. Decode: the model generates one output token at a time. At a high level, this step type E-Cali involves loading large matrices, e.g., model weights, into GPUs, which is limited by how quickly your hardware can load data into memory. Decoding is, therefore, memory bandwidth-bound. Figure 9.3 visualizes prefilling and decoding. Understanding inference optimization, 409. Figure 9.3. Autoregressive language models follow two steps for inference: prefill and decode. EOS denotes the end of the sequence token. Because prefill and decode have different computational profiles, they are often decoupled in production with separate machines. This technique will be discussed inference service optimization on page 440. The factors that affect the amount of prefilling and decoding computation in an LLM inference server, and therefore its bottlenecks, include context length, output length, and request batching strategies. Long context typically results in a memory bandwidth-bound workload, but clever optimization techniques, such as those discussed later in this chapter, can remove this bottleneck. As of this writing, due to the prevalence of the transformer architecture and the limitations of the existing accelerator technologies, many AI and data workloads are memory bandwidth-bound. However, future software and hardware advancements will be able to make AI and data workloads compute-bound. Online and batch inference APIs. Many providers offer two types of inference APIs, online and batch. Online APIs optimize for latency. Requests are processed as soon as they arrive. Batch APIs optimize for cost. If your application doesn't have strict latency requirements, you can send them to batch APIs for more efficient processing. Higher latency allows a broader range of optimization techniques, including batching requests together and using cheaper hardware. For example, as of this writing, both Google Gemini and OpenAI offer batch APIs at a 50% cost. 410, Chapter 9, Inference Optimization. 6. If you run an inference service, separating your inference APIs into online and batch can help you prioritize latency for requests where latency matters the most. Let's say that your inference server can serve only a maximum of X requests/second without latency degradation. You have to serve Y requests/second, and Y is larger than X. In an ideal world, users with less urgent requests can send their requests to the batch API, so that your service can focus on processing the online API requests first. Reduction and significantly higher turnaround time, i.e., in the order of hours instead of seconds or minutes. 6 Online APIs might still batch requests together as long as it doesn't significantly impact latency, as discussed in batching on page 440. The only real difference is that an online API focuses on lower latency, whereas a batch API focuses on higher throughput. Customer-facing use cases, such as chatbots and code generation, typically require lower latency, and, therefore, tend to use online APIs. Use cases with less stringent latency requirements, which are ideal for batch APIs, include the following: synthetic data generation, periodic reporting, such as summarizing Slack messages, sentiment analysis of brand mentions on social media, and analyzing customer support tickets, onboarding new customers who require processing of all their uploaded documents, migrating to a new model that requires reprocessing of all the data, generating personalized recommendations or newsletters for a large customer base, knowledge base updates by reindexing an organization's data. APIs usually return complete responses by default. However, with autoregressive decoding, it can take a long time for a model to complete a response, and users are impatient. Many online APIs offer streaming mode, which returns each token as it's generated. This reduces the time the users have to wait until the first token. The downside of this approach is that you can't score a response before showing it to users, increasing the risk of users seeing bad responses. However, you can still retrospectively update or remove a response as soon as the risk is detected. Understanding inference optimization, 411. 7. As discussed in prompt caching on page 443, it's common to know in advance the system prompt of an apply cation. It's just the exact user queries that are hard to predict. 8. In the early days of chatbots, some people complained about chatbots responding too fast, which seemed unnatural. See Lufthansa delays chatbots' responses to make it more human, Rick Crozier, IG News, May 2017. However, as people become more familiar with chatbots, this is no longer the case. A batch API for foundation models differs from batch inference for traditional ML. In traditional ML, online inference means that predictions are computed after requests have arrived. Batch inference means that predictions are pre-computed before requests have arrived. Pre-computation is possible for use cases with finite and predictable inputs like recommendation systems, where recommendations can be generated for all users in advance. These pre-computed predictions are fetched when requests arrive, e.g., when a user visits the website. However, with foundation model use cases where the inputs are open-ended, it's hard to predict all user prompts. 7. Inference performance metrics. Before jumping into optimization, it's important to understand what metrics to optimize for. From the user perspective, the central axis is latency. Response quality is a property of the model itself, not of the inference service. However, application developers must also consider throughput and utilization as they determine the cost of their applications. Latency, TTFT, and TPOT. Latency measures the time from when users send a query until they receive the complete response. For autoregressive generation, especially in the streaming mode, the overall latency can be broken into several metrics. Time to first token. TTFT measures how quickly the first token is generated after users send a query. It corresponds to the duration of the prefill step and depends on the input's length. Users might have different expectations for TTFT for different applications. For example, for conversational chatbots, the TTFT should be instantaneous. 8. However, users might be willing to wait longer to summarize long documents. For 12. Chapter 9, Inference Optimization. 9. Time between tokens, TBT, is used by LinkedIn, and intertoken latency, ITL, is used by NVIDIA. 10. An experiment by any scale shows that 100 input tokens have approximately the same impact on the overall latency as a single output token. Time per output token. TPOT measures how quickly each output token is generated after the first token. If each token takes 100 milliseconds, a response of 1000 tokens will take 100 s. In the streaming mode, where users read each token as it's generated, TPOT should be faster than human reading speed but doesn't have to be much faster. A very fast reader can read 120 milliseconds per token, so a TPOT of around 120 milliseconds, or 6 to 8 tokens/second, is sufficient for most use cases. Time between tokens and inter-token latency variations of this metric include time between tokens, TBT, and inter-token latency, ITL. 9 both measure the time between output tokens. The total latency will equal TTFT plus TPOT times number of output tokens. Two applications with the same total latency can offer different user experiences with different TTFT and TPOT. Would your users prefer instant first tokens with a longer wait between tokens, or would they rather wait slightly longer for the first tokens but enjoy faster token generation afterward? User studies will be necessary to determine the optimal user experience. Reducing TTFT at the cost of higher TPOT is possible by shifting more compute instances from decoding to prefilling and vice versa. 10. It's important to note that the TTFT and TPOT values observed by users might differ from those observed by models, especially in scenarios involving COT, chain of thought, or agentic queries where models generate intermediate steps not shown to users. Some teams use the metric time to publish to make it explicit that it measures time to the first token users see. Consider the scenario where, after a user sends a query, the model performs the following steps. 1. Generate a plan, which consists of a sequence of actions. This plan isn't shown to the user. 2. Take actions and log their outputs. These outputs aren't shown to the user. 3. Based on these outputs, generate a final response to show the user. Understanding inference optimization, 413. From the model's perspective, the first token is generated in step 1. This is when the model internally begins its token generation process. The user, however, only sees the first token of the final output generated in step 3. Thus, from their perspective, TTFT is much longer. Because latency is a distribution, the average can be misleading. Imagine you have 10 requests whose TTFT values are 100 milliseconds, 102 milliseconds, 100 milliseconds, 100 milliseconds, 99 milliseconds, 104 milliseconds, 110 milliseconds, 90 milliseconds, 3000 milliseconds, 95 milliseconds. The average TTFT value is 390 milliseconds, which makes your inference service seem slower than it is. There might have been a network error that slowed down one request or a particularly long prompt that took a much longer time to pre-fill. Either way, you should investigate. With a large volume of requests, outliers that skew the average latency are almost inevitable. It's more helpful to look at latency in percentiles, as they tell you something about a certain percentage of your requests. The most common percentile is the 50th percentile, abbreviated as P50, median. If the median is 100 milliseconds, half of the requests take longer than 100 milliseconds to generate the first token, and half take less than 100 milliseconds. Percentiles also help you discover outliers, which might be symptoms of something wrong. Typically, the percentiles you'll want to look at are P90, P95, and P99. It's also helpful to plot TTFT values against inputs lengths. Throughput and goodput. Throughput measures the number of output tokens per second an inference service can generate across all users and requests. Some teams count both input and output tokens in throughput calculation. However, since processing input tokens, pre-filling, and generating output tokens, decoding, have different computational bottlenecks and are often decoupled in modern inference servers, input and output throughput should be counted separately. When throughput is used without any modifier, it usually refers to output tokens. Throughput is typically measured as tokens/s, TPS. If you serve multiple users, tokens/s/user is also used to evaluate how the system scales with more users. Throughput can also be measured as the number of completed requests during a given time. Many applications use requests per second, RPS. However, for applications built on top of foundation models, a request might take seconds to complete, so many people use completed requests per minute, RPM, instead. Tracking this metric is useful for understanding how an inference service handles concurrent requests. Some providers might throttle your service if you send too many concurrent requests at the same time. 414, Chapter 9, Inference Optimization. Throughput is directly linked to compute cost. A higher throughput typically means lower cost. If your system costs $2 per hour in compute and its throughput is 100 tokens/s, it costs around $5. 556 per 1 M output tokens. If each request generates 200 output tokens on average, the cost for decoding 1K requests would be $1. 11. The prefill cost can be similarly calculated. If your hardware costs $2 per hour and it can prefill 100 requests per minute, the cost for prefilling 1K requests would be $0. 33. The total cost per request is the sum of the prefilling and decoding costs. In this example, the total cost for 1K requests would be $1. 11 plus $0. 33 equals $1. 44. What's considered good throughput depends on the model, the hardware, and the workload. Smaller models and higher-end chips typically result in higher throughput. Workloads with consistent input and output lengths are easier to optimize than workloads with variable lengths. Even for similarly sized models, hardware, and workloads, direct throughput comparisons might be only approximate because token count depends on what constitutes a token, and different models have different tokenizers. It's better to compare the efficiency of inference servers using metrics such as cost per request. Just like most other software applications, AI applications have the latency/throughput trade-off. Techniques like batching can improve throughput but reduce latency. According to the LinkedIn AI team in their reflection after a year of deploying generative AI products, LinkedIn, 2024, it's not uncommon to double or triple the throughput if you're willing to sacrifice TTFT and TPOT. Due to this trade-off, focusing on an inference service based solely on its throughput and cost can lead to a bad user experience. Instead, some teams focus on goodput, a metric adapted from networking for LLM applications. Goodput measures the number BER of requests per second that satisfies the SLO, software-level objective. Imagine that your application has the following objectives: TTFT of at most 200 milliseconds and TPOT of at most 100 milliseconds. Let's say that your inference service can complete 100 requests per minute. However, out of these 100 requests, only 30 satisfy the SLO. Then, the goodput of this service is 30 requests per minute. A visualization of this is shown in Figure 9.4. Understanding Inference Optimization, 415. Figure 9.4. If an inference service can complete 10 RPS but only 3 satisfy the SLO, then its goodput is 3 RPS. Utilization, MFU, and MBU utilization metrics measure how efficiently a resource is being used. It typically quantifies the proportion of the resource actively being used compared to its total available capacity. A common but often misunderstood metric is GPU utilization, and NVIDIA is party ally to blame for this misunderstanding. The official NVIDIA tool for monitoring GPU usage is NVIDIA SMI. SMI stands for System Management Interface. One metric this tool shows is GPU utilization, which represents the percentage of time during which the GPU is actively processing tasks. For example, if you run inference on a GPU cluster for 10 hours, and the GPUs are actively processing tasks for 5 of those hours, your GPU utilization would be 50%. However, actively processing tasks doesn't mean doing so efficiently. For simplicity, consider a tiny GPU capable of doing 100 operations per second. In NVIDIA SMI's definition of utilization, this GPU can report 100% utilization even if it's only doing 1 operation per second. If you pay for a machine that can do 100 operations and use it for only 1 operation, you're wasting money. NVIDIA SMI's GPU optimization metric is, therefore, not very useful. A utilization metric you might care about, out of all the operations a machine is capable of computing, is how many it's doing in a given time. This metric is called 416, Chapter 9, Inference Optimization. 11 people have cared about FLOP/S utilization for a long time, but the term MFU was introduced in the Palm paper, Chowdhury et al., 2022. MFU, model FLOP/S utilization, which distinguishes it from the NVIDIA GPU utilization metric. MFU is the ratio of the observed throughput, tokens/s, relative to the theoretical maximum throughput of a system operating at peak flop/s. If at the peak flop/s advertised by the chipmaker, the chip can generate 100 tokens/s, but when used for your inference service, it can generate only 20 tokens/s, your MFU is 20%. 11. Similarly, because memory bandwidth is expensive, you might also want to know how efficiently your hardware's bandwidth is utilized. MBU, model bandwidth utilization, measures the percentage of achievable memory bandwidth used. If the chip's peak bandwidth is 1 terabyte per second and your inference uses only 500 gigabytes per second, your MBU is 50%. Computing the memory bandwidth being used for LLM inference is straightforward. Parameter count times bytes/perm times tokens/s. MBU is computed as follows: parameter count times bytes/perm times tokens/s, / theoretical bandwidth. For example, if you use a 7B parameter model in FP16, 2 bytes per parameter, and achieve 100 tokens/s, the bandwidth used is 7B times 2 times 100 is equal to 700 GB/s. This underscores the importance of quantization, discussed in Chapter 7. Fewer bytes per parameter mean your model consumes less valuable bandwidth. If this is done on an A100-80 GB GPU with a theoretical 2 terabytes per second of memory bandwidth, the MBU is 700 gigabytes per second, / 2 terabytes per second, equals 70%. The relationships between throughput, tokens/s, and MBU and between throughput and MFU are linear, so some people might use throughput to refer to MBU and MFU. What's considered a good MFU and MBU depends on the model, hardware, and workload. Compute-bound workloads typically have higher MFU and lower MBU, while bandwidth-bound workloads often show lower MFU and higher MBU. Because training can benefit from more efficient optimization, e.g., better batching, thanks to having more predictable workloads, MFU for training is typically higher than MFU for inference. For inference, since prefill is compute-bound and decode is memory bandwidth-bound, MFU during prefilling is typically higher than MFU during decoding. For model training, as of this writing, an MFU above 50% is generally understanding inference optimization, 417. 12. Chipmakers might also be doing what I call peak flop/s hacking. This might run experiments in certain conditions, such as using sparse matrices with specific shapes, to increase their peak flop/s. Higher peak flop/s numbers make their chips more attractive, but it can be harder for users to achieve high MFU. Considered good, but it can be hard to achieve on specific hardware. 12. Table 9.1 shows MFU for several models and accelerators. Table 9.1. MFU examples from PaLM, Scaling Language Modeling with Pathways, Chowdhury et al., 2022. Model number of parameters, in billions, accelerator chips model flop/s utilization GPT-3 BV121. 3% go for 280 B4096 TPU V332. 5% Megatron Turing NLG 530 B2240 A130. 2% PaLM 540 B6144 TPU V446. 2% Figure 9.5 shows the MBU for the inference process using Llama 2-70B and FP16 on different hardware. The decline is likely due to the higher computational load per second with more users, shifting the workload from being bandwidth-bound to compute-bound. Figure 9.5. Bandwidth utilization for Llama 2-70B and FP16 across 3 different chips shows a decrease in MBU as the number of concurrent users increases. Image from LLM training and inference with Intel Gaudi 2 AI accelerators, Databricks, 2024. 418, Chapter 9, Inference Optimization. 13. In the 1960s, computers could run only one-layer neural networks, which had very limited capabilities. In their famous 1969 book Perceptrons, An Introduction to Computational Geometry, MIT Press, 2 AI pioneers, Marvin Minsky and Seymour Papert, argued that neural networks with hidden layers would still be able to do little. Their exact quote was, "Virtually nothing is known about the computational capabilities of this latter kind of machine. We believe that it can do little more than can a low-order perceptron." There wasn't sufficient compute power to dispute their argument, which was then cited by many people as a key reason for the drying up of AI funding in the 1970s. 14. There have been discussions on whether to rename the GPU since it's used for a lot more than graphics. John Petty, Chasing Pixels, July 2018. Jensen Huang, NVIDIA's CEO, said in an interview, Stratocarry, March 2022, that once the GPU took off and they added more capabilities to it, they considered renaming it to something more general like GPGPU, General Purpose GPU, or XGU. They decided against renaming because they assumed that people who buy GPUs will be smart enough to know what a GPU is good for beyond its name. Utilization metrics are helpful to track your system's efficiency. Higher utilization rates for similar workloads on the same hardware generally mean that your services are becoming more efficient. However, the goal isn't to get the chips with the highest utilization. What you really care about is how to get your jobs done faster and cheaper. A higher utilization rate means nothing if the cost and latency both increase. AI accelerators. How fast and cheap software can run depends on the hardware it runs on. While there are optimization techniques that work across hardware, understanding hardware allows for deeper optimization. This section looks at hardware from an inference perspective, but it can be applied to training as well. The development of AI models and hardware has always been intertwined. The lack of sufficiently powerful computers was one of the contributing factors to the first AI winter in the 1970s. 13. The revival of interest in deep learning in 2012 was also closely tied to compute. One commonly acknowledged reason for the popularity of AlexNet, Krzyzewski et al., 2012, is that it was the first paper to successfully use GPUs, graphics processing units, to train neural networks. 14. Before GPUs, if you wanted to train a model at AlexNet scale, you'd have to use thousands of CPUs, like the one Google released just a few months before AlexNet. Compared to thousands of CPUs, a couple of GPUs were a lot more accessible to PhD students and researchers, setting off the deep learning research boom. Understanding inference optimization, 419. 15. Matrix multiplication, affectionately known as MATMUL, is estimated to account for more than 90% of all float-ing point operations in a neural network, according to Data Movement is All You Need, a case study on optimizing transformers, Ivanov et al., AR14, v3, November 2021, and Scalable MATMUL Free Language Modeling, Zhu et al., AR14, June 2024. What's an accelerator? An accelerator is a chip designed to accelerate a specific type of computational workload. An AI accelerator is designed for AI workloads. The dominant type of AI accelerator is GPUs, and the biggest economic driver during the AI boom in the early 2020s is undoubtedly NVIDIA. The main difference between CPUs and GPUs is that CPUs are designed for general-purpose usage, whereas GPUs are designed for parallel processing. CPUs have a few powerful cores, typically up to 64 cores for high-end consumer machines. While many CPU cores can handle multi-threaded workloads effectively, they excel at tasks requiring high single-thread performance, such as running an operating system, managing I/O, input-output, operations, or handling complex, sequential processes. GPUs have thousands of smaller, less powerful cores optimized for tasks that can be broken down into many smaller, independent calculations, such as graphics rendering and machine learning. The operation that constitutes most ML workloads is matrix multiplication, which is highly parallelizable. 15. While the pursuit of efficient parallel processing increases computational capabilities, it imposes challenges on memory design and power consumption. The success of NVIDIA GPUs has inspired many accelerators designed to speed up AI workloads, including advanced microdevices, AMD's newer generations of GPUs, Google's TPU, Tensor Processing Unit, Intel's Habana Gaudi, Graphcore's Intelligent Processing Unit, IPU, Grok's Language Processing Unit, LPU, Cerebra's Wafer Scale Quant Processing Unit, QPU, and many more being introduced. While many chips can handle both training and inference, one big theme emerging is specialized chips for inference. A survey by Dezislavov et al. 2023 shares that inference can exceed the cost of training in commonly used systems, and that inference accounts for up to 90% of the machine learning costs for deployed AI systems. For 20 Chapter 9, Inference Optimization. 16 While a chip can be developed to run one model architecture, a model architecture can be developed to make the most out of a chip, too. For example, the transformer was originally designed by Google to run fast on TPUs and only later optimized on GPUs. As discussed in Chapter 7, training demands much more memory due to backpropagation and is generally more difficult to perform in lower precision. Furthermore, training usually emphasizes throughput, whereas inference aims to minimize latency. Consequently, chips designed for inference are often optimized for lower precision and faster memory access, rather than large memory capacity. Examples of such chips include the Apple Neural Engine, AWS Inferentia, and MTIA, Meta Training and Inference Accelerator. Chips designed for edge computing, like Google's Edge TPU and the NVIDIA Jetson Xavier, are also typically geared toward inference. There are also chips specialized for different model architectures, such as chip SPICY Alizade for the transformer. 16 Many chips are designed for data centers, with more and more being designed for consumer devices, such as phones and laptops. Different hardware architectures have different memory layouts and specialized compute units that evolve over time. These units are optimized for specific data types, such as scalars, vectors, or tensors, as shown in Figure 9.6. Figure 9.6. Different compute primitives. Image inspired by Chen et al. 2018. A chip might have a mixture of different compute units optimized for various data types. For example, GPUs traditionally supported vector operations, but many modern GPUs now include tensor cores optimized for matrix and tensor computation. TPUs, on the other hand, are designed with tensor operations as their primary compute primitive. To efficiently operate a model on a hardware architecture, its memory layout and compute primitives need to be taken into account. A chip specifications contain many details that can be useful when evaluating this chip for each specific use case. However, the main characteristics that matter across use cases are computational capabilities, memory size and bandwidth, and power consumption. I'll use GPUs as examples to illustrate these characteristics. Understanding inference optimization, 421. Computational capabilities are typically measured by the number of operations a chip can perform in a given time. The most common metric is flops/s, often written as flops, which measures the peak number of floating point operations per second. In reality, however, it's very unlikely that an application can achieve this peak flops/s. The ratio between the actual flops/s and the theoretical flops/s is one utilization metric. The number of operations a chip can perform in a second depends on the numerical precision. The higher the precision, the fewer operations the chip can execute. Think about how adding two 32-bit numbers generally requires twice the computation of adding two 16-bit numbers. The number of 32-bit operations a chip can perform in a given time is not exactly half that of 16-bit operations because of different chips optimization. For an overview of numerical precision, revisit Numerical Representations on page 325. Table 9.2 shows the flop/s specs for different precision formats for NVIDIA H100SXM chips. Table 9.2. Flop/s specs for NVIDIA H100SXM chips. Numerical precision teraflop/s, trillion flop/s, with sparsity TF32 tensor core and 989 BFLOAT 16 tensor core 1979 FP16 tensor core 1979 FP8 tensor core 3958. A recall from Chapter 7 that TF32 is a 19-bit, not 32-bit, format. Memory size and bandwidth. Because a GPU has many cores working in parallel, data often needs to be moved from the memory to these cores, and, therefore, data transfer speed is important. Data transfer is crucial when working with AI models that involve large weight matrices and training data. These large amounts of data need to be moved quickly to keep the cores efficiently occupied. Therefore, GPU memory needs to have higher bandwidth and lower latency than CPU memory, and thus, GPU memory requires more advanced memory technologies. This is one of the factors that makes GPU memory more expensive than CPU memory. For 22, Chapter 9, Inference Optimization. 17 lower-end to mid-range GPUs might use GDDR, Graphics Double Data Rate, memory. To be more specific, CPUs typically use DDR-SDRAM, Double Data Rate Synchronous Dynamic Random Access Memory, which has a 2D structure. GPUs, particularly high-end ones, often use HBM, High Bandwidth Memory, which has a 3D stacked structure. 17 an accelerator's memory is measured by its size and bandwidth. These numbers need to be evaluated within the system an accelerator is part of. An accelerator, such as a GPU, typically interacts with 3 levels of memory, as visualized in Figure 9.7, CPU memory, DRAM. Accelerators are usually deployed alongside CPUs, giving them access to the CPU memory, also known as system memory, host memory, or just CPU DRAM. CPU memory usually has the lowest bandwidth among these memory types, with data transfer speeds ranging from 25 GB per second to 50 GB per second. CPU memory size varies. Average laptops might have around 16 to 64 GB, whereas high-end workstations can have 1 TB or more. GPU High Bandwidth Memory, HBM, this is the memory dedicated to the GPU, located close to the GPU for faster access than CPU memory. HBM provides significantly higher bandwidth, with data transfer speeds typically ranging from 256 GB per second to over 1.5 TB per second. This speed is essential for efficiently handling large data transfers and high-throughput tasks. A consumer GPU has around 24 to 80 GB of HBM. GPU on-chip SRAM integrated directly into the chip. This memory is used to store frequently accessed data and instructions for nearly instant access. It includes L1 and L2 caches made of SRAM, and, in some architectures, L3 caches as well. These caches are part of the broader on-chip memory, which also includes other components like register files and shared memory. RAM has extremely high data transfer speeds, often exceeding 10 TB per second. The size of GPU SRAM is small, typically 40 MB or under. Understanding Inference Optimization, 423. 18 A main challenge in building data centers with tens of thousands of GPUs is finding a location that can guarantee the necessary electricity. Building large-scale data centers requires navigating electricity supply, speed, and geopolitical constraints. For example, remote regions might provide cheaper electricity but can increase network latency, making the data centers less appealing for use cases with stringent latency requirements like inference. Figure 9.7. The memory hierarchy of an AI accelerator. The numbers are for reference only. The actual numbers vary for each chip. A lot of GPU optimization is about how to make the most out of this memory hierarchy. However, as of this writing, popular frameworks such as PyTorch and TensorFlow don't yet allow fine-grained control of memory access. This has led many AI researchers and engineers to become interested in GPU programming languages such as CUDA, originally Compute Unified Device Architecture, OpenAI's Triton, and ROCm, Radeon Open Compute. The latter is AMD's open-source alternative to NVIDIA's proprietary CUDA. Power consumption chips rely on transistors to perform computation. Each computation is done by transistor switching on and off, which requires energy. A GPU can have billions of transistors. An NVIDIA A100 has 54 billion transistors, while an NVIDIA H100 has 80 billion. When an accelerator is used efficiently, billions of transistors rapidly switch states, consuming a substantial amount of energy and generating a non-trivial amount of heat. This heat requires cooling systems, which also consume electricity, adding to data centers' overall energy consumption. Chip energy consumption threatens to have a staggering impact on the environment, increasing the pressure on companies to invest in technologies for green data centers. An NVIDIA H100 running at its peak for a year consumes approximately 7,000 kilowatt-hours. For comparison, the average U.S. household's annual electricity consumption is 10,000 kilowatt-hours. That's why electricity is a bottleneck to scaling up compute. 18424, Chapter 9, Inference Optimization. Accelerators typically specify their power consumption under maximum power draw or proxy metric TDP. Thermal design power. Maximum power draw indicates the peak power that the chip could draw under full load. TDP represents the maximum heat a cooling system needs to dissipate when the chip operates under typical workloads. While it's not an exact measure of power consumption, it's an indication of the expected power draw. For CPUs and GPUs, the maximum power draw can be roughly 1:1. 5 times the TDP, though the exact relationship varies depending on the specific architecture and workload. If you opt for cloud providers, you won't need to worry about cooling or electricity. However, these numbers can still be of interest to understand the impact of accelerators on the environment and the overall electricity demand. Selecting accelerators. What accelerators to use depends on your workload. If your workloads are compute-bound, you might want to look for chips with more flops/s. If your workloads are memory-bound, shelling out money for chips with higher bandwidth and more memory will make your life easier. When evaluating which chips to buy, there are 3 main questions. Can the hardware run your workloads? How long does it take to do so? How much does it cost? Flop/s, memory size, and memory bandwidth are the 3 big numbers that help you answer the first 2 questions. The last question is straightforward. Cloud providers' pricing is typically usage-based and fairly similar across providers. If you buy your hardware, the cost can be calculated based on the initial price and ongoing power consumption. Understanding inference optimization. 425. Inference optimization. Inference optimization can be done at the model, hardware, or service level. To illustrate their differences, consider archery. Model-level optimization is like crafting better arrows. Hardware-level optimization is like training a stronger and better archer. Service-level optimization is like refining the entire shooting process, including the bow and aiming conditions. Ideally, optimizing a model for speed and cost shouldn't change the model's quality. However, many techniques might cause model degradation. Figure 9.8 shows the same llama model's performance on different benchmarks, served by different inference service providers. Figure 9.8. An inference service provider might use optimization techniques that can alter a model's behavior, causing different providers to have slight model quality variations. The experiment was conducted by Cerebras, 2024. Since hardware design is outside the scope of this book, I'll discuss techniques at the model and service levels. While the techniques are discussed separately, keep in mind that, in production, optimization typically involves techniques at more than one level. Model optimization. Model-level optimization aims to make the model more efficient, often by modifying the model itself, which can alter its behavior. As of this writing, many foundation models follow the transformer architecture and include an autoregressive language model component. These models have 3 characteristics that make inference resource-intensive: model size, autoregressive decoding, and the attention mechanism. Let's discuss approaches to address these challenges. 426, Chapter 9, Inference Optimization. Model compression. Model compression involves techniques that reduce a model's size. Making a model smaller can also make it faster. This book has already discussed 2 model compression techniques: quantization and distillation. Quantization, reducing the precision of a model to reduce its memory footprint and increase its throughput, is discussed in Chapter 7. Model distillation, training a small model to mimic the behavior of the large model, is discussed in Chapter 8. Model distillation suggests that it's possible to capture a large model's behaviors using fewer parameters. Could it be that within the large model, there exists a subset of parameters capable of capturing the entire model's behavior? This is the core concept behind pruning. Pruning, in the context of neural networks, has 2 meanings. One is to remove entire nodes of a neural network, which means changing its architecture and reduce its number of parameters. Another is to find parameters least useful to predict tie-ins and set them to 0. In this case, pruning doesn't reduce the total number of parameters, only the number of non-zero parameters. This makes the model more sparse, which both reduces the model's storage space and speeds up computation. Pruned models can be used as is or be further fine-tuned to adjust the remaining parameters and restore any performance degradation caused by the pruning process. Pruning can help discover promising model architectures, Liu et al., 2018. These pruned architectures, smaller than the pre-pruned architectures, can also be trained from scratch, Zhu et al., 2017. In the literature, there have been many encouraging pruning results. For example, Frankel and Carbon, 2019, showed that pruning techniques can reduce the non-zero parameter counts of certain trained networks by over 90%, decreasing memory footprints and improving speed without compromising accuracy. However, in practice, as of this writing, pruning is less common. It's harder to do, as it requires an understanding of the original model's architecture, and the performance boost it can bring is often much less than that of other approaches. Pruning also results in sparse models, and not all hardware architectures are designed to take advantage of the resulting sparsity. Weight-only quantization is by far the most popular approach since it's easy to use, works out of the box for many models, and is extremely effective. Reducing a model's precision from 32 bits to 16 bits reduces its memory footprint by half. However, we're close to the limit of quantization, we can't go lower than 1 bit per value. Distillation is also common because it can result in a smaller model whose behavior is comparative to that of a much larger one for your needs. Inference optimization, 427. 19 Each token generation step necessitates the transfer of the entire model's parameters from the accelerator's high-bandwidth memory to its compute units. This makes this operation bandwidth-heavy. Because the model can produce only one token at a time, the process consumes only a small number of flops/s, resulting in computational inefficiency. Overcoming the autoregressive decoding bottleneck as discussed in Chapter 2, autoregressive language models generate one token after another. If it takes 100 milliseconds to generate one token, a response of 100 tokens will take 10s. 19 This process is not just slow, it's also expensive. Across model API providers, an output token costs approximately 2 to 4 times an input token. In an experiment, AnyScale found that a single output token can have the same impact on latency as 100 input tokens, Caddis et al., 2023. Improving the autoregressive generation process by a small percentage can significantly improve user experience. As the space is rapidly evolving, new techniques are being developed to overcome this seemingly impossible bottleneck. Perhaps one day, there will be architectures that don't have this bottleneck. The techniques covered here are to illustrate what the solution might look like, but the techniques are still evolving. Speculative decoding. Speculative decoding, also called speculative sampling, uses a faster but less powerful model to generate a sequence of tokens, which are then verified by the target model. The target model is the model you want to use. The faster model is called the draft or proposal model because it proposes the draft output. Imagine the input tokens are x1, x2, xt1. The draft model generates a sequence of k tokens xt plus 1, xt plus 2, xt plus k. 2. The target model verifies these k generated tokens in parallel. 3. The target model accepts the longest subsequence of draft tokens, from left to right, which the target model agrees to use. 4. Let's say the target model accepts j draft tokens, xt plus 1, xt plus 2, xt plus j. The target model then generates one extra token, xt plus j plus 1. The process returns to step 1, with the draft model generating k tokens conditioned on x1, x2, xt, xt plus 1, xt plus 2, xt plus j. The process is visualized in Figure 9. If no draft token is accepted, this loop produces only one token generated by the target model. If all draft tokens are accepted, this loop produces k plus 1 tokens, with k generated by the draft model and 1 by the target model. For 28, Chapter 9, Inference Optimization.